4. Okay, so let's talk about elimination versus addition. In chapter 7, we talked exclusively about SN1, SN2, E1, and E2 reactions. So we looked at all kinds of elimination reactions where we could make an alkene. However, in this chapter, chapter 8, we're focusing on addition. And it says here that elimination and addition are actually equilibrating reactions, and which side is going to be favored will depend on temperature. Now, why would that be? Well, if we look at it, if we look at the difference between the elimination and the addition, what we have to look at is delta G. When is the reaction spontaneous for addition, and when is the reaction spontaneous for elimination? Remember that in order for a reaction to be spontaneous, the delta G has to be negative. Now, let's take a look here. So what it says is, first of all, if we look at an addition reaction from the point of view of enthalpy, so enthalpy, remember, is H, and if we look at it from the point of view of H, when you do an addition reaction, check out what's happening. You're breaking a pi bond and a sigma bond, and then you end up forming 2 sigma bonds. Now, what do we know about sigma versus pi bonds? We know that sigma bonds are stronger than pi bonds. So if we use our formula that the enthalpy of the reaction, so if we use the formula, we'll put here delta H, I'll just make it simple. We'll say the enthalpy of the reaction is going to be the enthalpy of the bonds broken but minus bonds. Oh, I already have the formula here. I didn't even notice. So here it is right here. So if we use this formula, bonds broken minus bonds formed, since the bonds formed are stronger, we end up with a negative delta H. So our enthalpy is negative in an addition reaction. Okay, but remember that we have to consider that delta G is equal to delta H minus T delta S. So far, all we've looked at is delta H, and we know that delta H is negative. But what about all of this? Well, let's take a look at that. Now, we're going to take a look at entropy. So entropy, remember, is S. If I'm starting it with 2 things and I end up with 1 thing, what's the sign of my change in entropy? My delta S is going to be negative. So I'll write negative like that. Why? Because I'm going from 2 things which are more disordered to something that is more ordered. So I'm decreasing my entropy. My entropy value is negative. So now we're going to put all of that together into the formula. Let me write it out again. I'm going to scribble it right here. So we'll put delta G is equal to delta H minus T delta S. We already said that delta H is negative, and then we have subtract. Our T is always positive, so we'll put positive times our delta S, which is negative. So now, if you make that a little simpler, you've got a negative subtract a negative. So if you have a negative subtract a negative, it's like taking a negative and adding something to it. So when is delta G going to be negative? Delta G will be a negative number when the temperature is a small number, right? If this is really low, you take a small positive number and multiply it by the negative number, you get something that's small, and so this still stays negative. And that is why when we do an addition reaction, it's going to be spontaneous at low temperature. Whereas if you look at the sign of delta G, if you jack up the temperature super high so that you have a really big positive number, then you take a negative and you're subtracting a really big negative, which is going to render delta G positive. And so at a high temperature, the elimination is going to predominate. Again, to rehash, what we did is we just looked at the formula for Gibbs free energy, or change in Gibbs free energy, and we determined that based on the sign of delta H, which is negative, and delta S, which is negative, for our addition reaction, at lower temperatures, the reaction addition is going to be favored, or it's going to be spontaneous. Whereas if you turn up the temperature too high, then elimination is going to be the spontaneous reaction. Give me a thumbs up if you follow me on this. Lower temperature is going to be preferred when we do an addition reaction. Cool, great. Yeah, it's kind of fun to apply a little bit of Gen Chem too to your organic chemistry. Kind of understand, why is this happening? Why do addition reactions occur at low temperatures like we see right here? Check this out. Hydrohalogenation. Hydro stands for a hydrogen. You could probably figure that out without me telling you. So hydro is a hydrogen, and halogen, the halogens that we're going to look at will be chlorine, bromine, and iodine. So we're talking about adding HCl, HBr, or HI across a double bond. So let's take a look at this first reaction here. We've got cis, so this is Cis3 Hexane, this molecule right here, and we're treating it with some HBr. What's happening? Well, we've got two carbons in the double bond, don't we? We've got this carbon in blue, this carbon in red. There's no differentiation between the two because there's a plane of symmetry in the molecule. But either way, on the blue carbon, let's say, that's not blue. On the blue carbon, you've already got a hydrogen on there, right? You've got a hydrogen. So now you're adding a second hydrogen. You're adding the hydrogen from the HBr. So we have the original hydrogen, and then you've added a hydrogen from the HBr molecule, and you've added the bromine to the carbon in red. Hydrohalogenation, adding a hydrogen and a halogen. Now, this question is rather simple because, again, there's an axis of symmetry here, a plane of symmetry in the molecule. However, if we, and I didn't even put in this hydrogen, which I think you all know there's another hydrogen here. But anyhow, what happens if the alkene isn't symmetrical? If you look at this alkene that I have on the bottom right that has the sign that says vinylic positions on it, on one of the vinylic carbons, you have one hydrogen, but on this one here that I have the circle around, there are no hydrogens. Where does the halogen go? Where does the hydrogen go when we do hydrohalogenation on an unsymmetrical alkene? Well, if you read ahead in the book, you would know the answer to that. And we call this a regioselective reaction. We say that the hydrogen addition to one carbon over the other preferentially is regioselective. And what we say is that hydrohalogenation is regioselective for what is called Markovnikov addition. And you need to be fully aware of what Markovnikov addition is as an organic chemistry student. The name Markovnikov lives on in infamy for organic chemists, and it's never going to go away until you finish organic chemistry 2. You'll be hearing it constantly from your instructor. What's the rule? Markovnikov addition is this. In 1869, Markovnikov noticed that hydrogen atoms tend to go to the carbon that's already bearing more hydrogen atoms. The way my students like to remember this is this way. The rich in H's, okay? The rich get richer. So you look at the two vinylic carbons. Whichever one is richer in hydrogens, it's the one that's going to take the hydrogen from your HBr, your HCl, or your HI. And that's what's happening here. That is where the hydrogen is being installed. The rich are getting richer, and the bromine or the chlorine or the iodine is going to end up on the carbon that has less hydrogens on it. Put another way, instead of thinking about it from the point of view of the hydrogens, is you could say the opposite. You could say the halogen, whether it is a chlorine, a bromine, or an iodine, generally speaking, is going to be installed at the more substituted carbon. So the rich in hydrogens get richer in hydrogens, or you could say the more substituted carbon is the one that takes on the halogen. Either way is perfectly reasonable. Now, if you're wondering, man, is this reaction regioselective for, the rich getting richer in hydrogens all the time? Well, no. What happens is if you try the reaction of the addition of HBr, let's say, this molecule, to an unsymmetrical alkene, and you have a peroxide. This, where it says ROOR, this is called an organic peroxide. So I'll just put here peroxide. It's a new functional group for you. It's not hydrogen peroxide. Hydrogen peroxide is H2O2. That's something else. This is an organic peroxide with R groups, carbon-based groups. When you have a peroxide dissolved in your flask, what you get is what we call anti-Markovnikov. Now the rich don't get richer. Check it out. This carbon is richer in hydrogens, and this is now the one that's going to take on the halogen. So we call that anti-Markovnikov addition. Now, if we always end up with a different regioisomer, or sorry, a different regioselectivity, what that tells you is that the mechanism must be different. And this is a mechanism that we cover at the very end of the course. We cover it in section 10.10. So the second to last week, or the last week of class, we cover the reaction mechanism of Markovnikov addition. However, in this chapter, we're going to cover this mechanism of Markovnikov addition in detail. To summarize, we can control the regioselectivity of HBr addition. If we have HBr added to an unsymmetrical alkene, no peroxides in our flask, we find out that we get Markovnikov addition. The rich get richer. Whereas if we have peroxides in our flask, again, this is called a peroxide, we get anti-Markovnikov addition. Give me a thumbs up if you just follow me on the concept of the rich get richer, Markovnikov. If the if the carbon that's richer in hydrogens takes the bromine or the chlorine or the iodine, we call it anti-Markovnikov addition. Okay, there we go. Well, we're actually going to talk about why you can do Markovnikov addition with HCl, HBr, and HI. But with anti-Markovnikov, we're only going to see it with HBr. And again, we're going to cover that in chapter 10, why that is. So with that in mind, let's see if we can draw the major product for these reactions. Both of these are unsymmetrical alkenes, and we're adding HBr. The first example, no peroxides. And the other ones says we're using peroxides. All right. So let's take a look at the first one. I'm going to label this carbon in blue, and I'm going to label this carbon in red. Could anybody tell me on which carbon will the, what's going on there? Oh, there we go. It was there. Okay. On which carbon is the bromine going to go? Will the bromine go on the blue carbon or the red carbon? The bromine go on the blue carbon or the red carbon? Exactly. It's going to go on the blue one, isn't it? Because it's more substituted. So we'll put here more substituted. Therefore, my bromine is going to go on that carbon. So let's draw my 5 atoms in the ring. This is my carbon in blue. This is my carbon in red. It already has a hydrogen on it, which is going to be here. But now it's going to have the other hydrogen, and the carbon is going, that's in blue, is going to have the bromine. So this is the same thing as just writing this, which would be a lot prettier, this compound. Give me a thumbs up if you follow me on the Markovnikov product. So this is what we call the Markovnikov addition product. Okay, cool. Well, let's take a look at the next one, which is anti-Markovnikov. So now I have the blue carbon, and I have the red carbon, which has one hydrogen. So let's redraw the chain. Got my methyl group here. This is my carbon in blue. This is my carbon in red. So if it's anti-Markovnikov, now the bromine is going to go on the carbon that has the hydrogen attached to it already. So I'm going to have my bromine here, and I'm going to have my other hydrogen over here. Now, if I write that out in a nice bond line structure, it's going to look like this. Oops. What happened there? Bromine. So this is the anti-Markovnikov product. I'll just use Mark period for short. Give me a thumbs up if you follow me on anti-Markovnikov. So you're down with Markovnikov and anti-Markovnikov. Okay, again, if you have a very inquiring mind, and I know a lot of my students just need to know, how does this work and how does that work? And that's great. We're going to cover this in detail, why this happens, and this we're going to look at in detail in chapter 10. So if you're dying to learn about what the peroxides do, you could go ahead and read chapter 10, and that would give you all the information that you need to know about that. Well, let's answer the question. why is it that we get Markovnikov addition? Do you guys remember carbocation stability? Because that is going to give you the answer. Check this out. The first step in the hydrohalogenation is a proton transfer, right? Our alkene is acting like a base. This is an acid. So we have a proton transfer in the first step, and we end up forming a carbocation. Now notice that this is regioselective, right? The carbon that's richer in hydrogens, which is this one, where this hydrogen atom is here. Why can't I draw a straighter bond than that? There we go, it's a little better, okay? The hydrogen atom that has the hydrogen is the one that's taking the hydrogen, right? This is Markovnikov regioselectivity, and then the bromine is going and attacking the carbocation so that we end up with the Markovnikov product, right? This is the Markovnikov product. Now, what would happen if it was anti-Markovnikov, which it's not? I'll write it in blue. This is what would happen. Check this out. If I draw the alkene, okay, here's my proton transfer step. Son of a gun. Here's my proton transfer step. Like this, okay? Now I'm going to draw it so that the proton is going on the more substituted carbon. So this would be anti-Markovnikov. So this is incorrect, okay? This is an incorrect mechanism. I'm saying if this happened hypothetically, what would we get? We'd get this, where the hydrogen would be added here, and we'd have a carbocation here. Then the bromide could come in as a nucleophile, okay, and it could attack the carbocation, which would give us this compound, where we have the bromine here, and we have the hydrogen over here. So this is anti-Markovnikov. Could anybody tell me what the problem is, or why the anti-Markovnikov is not going to be the major product based off of this mechanism? Something that anybody notices that's different between the two of these? A major difference?
Would this be because of like carbocation stability?
Absolutely. Clinton, I couldn't have said it better myself, okay? Okay, you step up to the mic and do your thing, you know? Absolutely. So what Clinton said is this. He said, look, Mr. Dion, you've got a tertiary carbocation here, and you've got a secondary carbocation here. What you told me was that a tertiary carbocation was way more stable than a secondary, then a primary, and then a methyl. And so since this carbocation is so much more stable than this thing, that is why Markovnikov products are formed preferentially. It's based on nothing more than the activation energy to do the proton transfer is going to be much lower, much, much lower. And then you end up with a more substituted compound. So that's more stable too. It's a double whammy. Now I'm getting ahead of myself, but I can't help it. Okay. And I knew you'd be able to figure it out. If you look at the reaction coordinate diagram, you see that the rate determining step is the proton transfer, right? Okay. This is the activation energy here. But you can imagine that if you wanted to make that secondary carbocation that's up here, right, then the activation energy is going to be way higher to make that secondary carbocation, which is higher in energy. And that is the reason why we get Markovnikov addition. So recall, there's two possible products, Markovnikov, anti-Markovnikov. Like Clinton just said, the reason why we don't get the anti-Markovnikov is because it proceeds through a less stable carbocation. Put another way, and I'm just repeating myself, but whatever, I'm the instructor. The reason why we get Markovnikov is because tertiary carbocation is most stable. There we go. Give me a thumbs up if you follow me on the rationale. Secondary versus tertiary. Tertiary is more stable. Beautiful. That's it, my friends. That's it, man. I've seen people in their PhD defense who are asked about Markovnikov addition. So it is a very important concept in organic chemistry. And you're giving me a thumbs up and telling me, you know what? I'm with you most of the way already the first time I heard it. Well, that's a good thing. Okay, very important concept. And again, it's going to come up repeatedly in organic chemistry. This is what I tried to sketch a few minutes ago, where I just said this is the first step. This is just the proton transfer. Okay, that's not right. Where's my pen? This is just the first step. The son of a gun. proton transfer. And I said the activation energy to get to the secondary carbocation is higher and it's less stable. So that's not good. And then, yeah, so that's enough about that. I got one more thing to say about hydrohalogenation, which is stereochemical considerations that we have to take into account. And then we're going to talk about carbocation rearrangements, and that'll be it for hydrohalogenation. So check this out. I know that everybody who's hearing the sound of my voice, when we went back, let's go back all the way here, okay? If I had asked any of you, what's the hybridization of these carbocations? What would you have said? What's the hybridization of a carbocation? Is it sp, sp2, sp3? I'll give you a clue. It's not sp3d2. That's a joke. Okay, not even close. What's the hybridization of a carbocation? We've seen it repeatedly. It's got an empty p orbital. It's sp2. A carbocation is sp2 hybridized, okay? All organic chemists need to know that a carbocation is sp2 hybridized. What's the molecular geometry of an sp2 hybridized carbon? It's trigonal, planar. It's flat, like a pancake. So if we think about the carbocation that's formed, right, when you add HCl across this double bond in a Markovnikov fashion, the rich are going to get richer, so you're going to end up with this carbocation. Now your nucleophile, which is the chloride, can come in and it can attack from the front face and give you the R, or it could go in and it could attack from the back and give you the S. It can go either way because that sp2 hybridized carbon is flat like a pancake. Give me a thumbs up if you follow me on the sp2 trigonal planar, and if it's flat, your nucleophile can give you a mixture of R and S in this case. Okay, cool. I have it drawn right here. This obviously comes straight out of the textbook, but the idea is that when you have a carbon that's sp2 hybridized, that it's got an empty p orbital, right? This is an empty p orbital with nothing in it. That's where the positive charge comes from. And so the nucleophile can attack from the top face of the molecule or the bottom face of the molecule, and that's why you end up with a pair of enantiomers in this case. Okay, you could be diastereomers depending on the situation, but the idea that you need to be aware of is that the nucleophile can attack either face of the molecule, or I should say either face of the carbocation with equal probability. You're going to get a 50-50 mixture of stereoisomers. All right. Now, one more concept before we try some practice, and that is the carbocation rearrangement. Take a look at this alkene here. If we took that and we treated it with HCl, it's going to react in a Markovnikov fashion. We look at this carbon, it's got 2 hydrogens, and this one only has 1 hydrogen. So the rich are going to get richer, and you're going to produce a secondary carbocation. What did I teach you about carbocation rearrangements? I said if they can occur, they will. And this secondary carbocation can undergo a hydride shift to produce a tertiary carbocation. So what that means is that the nucleophile could attack this carbocation. It's not written on this slide, but the nucleophile, where's my chloride? I'll just draw another chloride in here. The chloride could also attack this carbocation, which would give you this compound. And so really, you're going to end up with a mixture of both of these compounds, and you will not just get one thing. Now, they're normally not going to be formed in a 50-50 ratio, like 1-to-1. You'll get a mixture of both, and in this case, it says you get a 60-40 ratio. You get mostly the rearrangement product, but the bottom line is that students have to be always on the lookout for a hydride or a methyl shift rearrangement, because when carbocation rearrangements can occur, they will happen. Molecules always do what they want to do, and they always want to rearrange to become more stable. So, with all that in mind, let's take a look at a practice problem. This is question 8.5. It might be question 8.8. Let me just double check here. Oh, So let me double check the number here. I think I have it right. So it is 8 No, it's not 8. Yeah, it's 8.5. I'm right. Yep, I get it right. Okay. Predict the products for each of the following reactions. In some cases, the reaction produces a new chiral center, while in other cases, it makes no new chirality center. Now, it doesn't ask us to draw a mechanism, but I figure, what the hey, we're here. Let's give it a shot. We've got our HBr. I'm going to quiz you on this a couple more times. Let's say I highlight this carbon in red, this carbon in blue. Which carbon is going to take the hydrogen? Would it be the red carbon or the blue carbon? Which one will take the hydrogen from my HBr molecule? I know you know the answer. I see, I knew it. Okay. Teach the best. Exactly. It's going to be the red carbon because the rich get richer. Exactly. So I'm going to just erase those, and I'm going to say, here comes my proton transfer. Oops, I can do it better than that. Here goes my proton transfer. And let's draw the carbocation that's formed. So we're going to end up with this carbocation right here, like this. Is that carbocation going to rearrange? Yes or no? It's a tertiary carbocation. Is there any reason for that to rearrange? No, exactly. So now my bromide is going to come in and it's going to do a nucleophilic attack, but it could do it from the back face of the molecule, which would give me this compound where the bromide is in the back and the methyl group is out in front, or the bromide could come in from the front face. I could draw it prettier than that. Or it could come in from the front face of the molecule like this, which would give me the bromide coming out in front and the methyl group coming in back. What's the stereochemical relationship between the compound in red and the compound in blue? Could anybody tell me what that is? You say they're diastereomers, identical. All I've done is invert one stereocenter. And so these two molecules would be, these are enantiomers. All right, yeah, exactly. My students are all 100% correct on that. So now what I'd like to do is take a short break. I would like you to try these two questions, and then you can see that the next slide is another question where it asks you not about what are the products, it gives you the products, and it asks you what would be the reagents. So I want you to give this question a try, the last two parts, and I want you to give this question a try. And then after that, we're going to move on to acid catalyzed hydration reaction. So now we're going to look at adding water across a carbon-carbon double bond, which I can encourage you, if you understood Markovnikov regioselectivity, hydration also occurs via Markovnikov regioselectivity.